So my name is Lu. Today I'm going to talk about work of training very deep neural network on corrupted label. So this is joint work with Google AI, Google Cloud, and Stanford University. So basically, let's first look at some introduction. We all know that in order to train a better model, we should train a very deep network on big data. However, the big data often come with noise or corrupted label. If you look at, for example, data set, YouTube 8 million, OpenImage, Flickr 100 million, they all have like noise label. So on the other hand, a recent study showed by John said that, as this is mentioned by the previous presentation, like the deep network are very good at overfitting the noisy label. So if you look at the plot on the left, so even though you feed into completely random label, this deep network can give you zero training loss. But if you look at the generation performance on the test data, it performed very poorly. So the reason for that is like probably the deep network are memorizing the noisy label instead of learning some meaningful representation. So this actually creates a very serious problem if you think about it. On one hand, we need big data to train very deep network. On the other, this deep network can be sensitive to the noise in this big data. That motivated us to study how to train a very deep network on noisy data to improve the generation performance. So when we say the deep network, we mean very deep network, convolution network. It has a few hundred layers, tens of millions of model parameters, and take days to train on 100 plus GPU. So the noisy data we mean, so the training label can be noisy or corrupted, which means can include incorrect label or missing labels. So fortunately, the community has realized the importance of this problem, and there has been a number of work proposed to tackle this problem. However, different from all previous work, in this paper, we focus on training very deep convolution neural network from scratch. So we propose our method based on curriculum learning, and here's some background. In traditional supervised learning, so we have a training image, we just randomly shuffle each example and treat them equally. This can be problematic if you have noise in the training because it can confuse the model. So the curriculum learning is motivated by human learning. It actually tries to learn example with focus. So in order to do that, we introduce a teacher to determine the weight and the timing to learn each example. So basically here, even you have a teacher, it will output some curriculum based on which we can order the training example and weight them accordingly. So now the question is, how do you get this curriculum? Okay, one way to do this is by introducing a latent variable to your loss function, is VI here, which used to times the sample loss. And at the same time, we also introduce a regularization term, capital G, over this latent variable. And for each capital G regularization term, if you do some math, you will get some optimal way to compute the sample weight, VI star here. So we call this weighting scheme. So here I just show one example called self-paced learning, and it favors example of smaller loss. And actually in the literature, there exists a bunch of this way to define different curriculum, and they have been very successful and solve a variety of problems in both computer vision and machine learning community. Here's just some example. But in either case, in both, so they specify the curriculum either by specifying the regularization term, capital G, or by directly specifying how to weight each example, V star. So in both cases, it's actually define a curriculum by a function. So here in this work, we're wondering, can we learn a curriculum by a neural network just from the data? So answer is yes. So in order to do that, we propose a framework called mentornet. So that here we implement each curriculum as a neural network. We call this mentornet. Okay, so the mentornet is used to supervise the training of the base network called studentnet. In training, mentornet and studentnet are learned together jointly, where the mentornet extracts the input feature from the mini batch and output the weight for studentnet to learn. At the test time, the studentnet makes prediction alone without any mentornet. Okay, there are two ways to learn a mentornet. The first way we call predefine. The goal here is to approximate existing curriculum. So in order to do that, we enumerate the input space of the mentornet, and then because we can compute the optimal weight by some closed form solution in the existing curriculum, we directly minimize the distance between the optimal weight and the mentornet output. The second way to learn the mentornet is called data-driven. So here we want to discover new curriculum completely from the data. So in order to do that, we assume we have a small number of examples with clean label available. So we will then label this example, give them 1 weight if it's a clean label, otherwise 0. We input this example to the student net and minimize the cross-entropy loss between this optimal weight and mentornet output. Okay, sometimes it is impossible to get such clean label on your data. So in this case, actually, we can learn the mentornet from a data set, for example, CFAR10, and then use it on another data set, for example, CFAR100. We actually, in the paper, we propose an algorithm which can train this mentornet and student together and through mini-batch stochastic gradient descent, and we show some good theoretical property about the model convergence under standard assumption. Okay, an interesting question to ask is why does it work? Okay, so by some theoretical analysis in the paper, we show that by introducing such a mentornet, you're optimizing a latent robust version of your loss function, which plays a similar role to the robust M estimator, including the well-known Huber loss and the log sum penalty. So basically, because we are dealing with a noisy label, having such a robust object function is very useful. For example, here in this figure, the x-axis represents the sample loss, and the y-axis represents the objective function value. And we see that all these curves are robust loss. But here, the blue one, blue curve indicates the learned objective function by our data-driven mentornet. Okay, let's look at some experiment result. So we test our result first on 3 data sets, CFAR10, CFAR100, and ImageNet, with 3 student net, inception ResNet 101 and inception ResNet V2. Here this table shows the number of parameters and also the validation accuracy on each task. So then we first tested on some synthetic noise corrupted label. So basically here we use, so for each label, we randomly flip it to a uniform random class with probability P, where the P is called noise fraction. Here we show some example of 20, 40, and 80% noise fraction. Okay, first let's look at some result on CFAR10 and CFAR100. And here we compare to our method to a number of baseline methods. So first we observe that the mentornet outperform all the existing baseline methods significantly. And also, if we look at it, so the data-driven mentornet, which is annotated as a mentornet DD, is better than the pre-specified mentornet, which is mentornet PD. So we conduct similar experiments on ImageNet under 40% noise fraction, where we observe a similar pattern, where this mentornet outperformed all the baseline methods significantly and by up to 4% in terms of P at 1. And I want to emphasize here, we separate all this existing regression technique, such as weight decay, dropout, and data augmentation, and you can read that in the paper. So then we actually go down to a real-world noise data. So here we consider a data set called Web Vision. It includes 2.4 million images and over 1,000 classes. So these images are crawled from Flickr and Google search. So this represents a real-world noisy label. Here I want to emphasize these images are like of real-world noisy label, and we do not know what is the noise fraction in this data set. Okay, so we compare our method to some existing method on this benchmark, and we achieve the best published result on this benchmark. So we believe that this result, together with all previous results we have seen, substantiates that mentornet is beneficial for training the very deep network on noisy label. So here's the conclusion. So today we discussed a novel way to train very deep network on noisy data, and there's some interesting observation. We found that the generation performance of the deep network can be improved by learning another network. In this work we call this mentornet to supervise the training of their base network. Secondly, we propose a novel method to perform curriculum learning or self-paced learning for this deep network through mini-batch stochastic gradient descent, and we have some good theoretical property about this algorithm. The code will be available soon on Google GitHub, and please come to our poster 113. Thank you.
Thank you. Any questions?
Very nice work, thank you. So on the web vision, maybe I'm missing something, but how do you have the ground truth? If, so you mentioned on the one hand you don't know the noise proportion. On the other hand, you have some
Yeah,
evaluation statistics. So
That's a good question. So in this data, because this has the same vocabulary as the ImageNet, so one way you can test it on a standard ImageNet validation set. Another thing is like they organize the challenge. They have some manually labeled test set to evaluate your method. Yeah.
thank you.
Want to ask?
Just one quick question, like, the mentornet, you mentioned that you're doing 10% of the sample, but what is the size of the mentornet when you, for example, when you're using that to guide the original network? What is the size of the mentornet compared to the original net?
So mentornet is pretty small. Actually, we found in our paper the architecture of the mentornet by itself is not very important. So you can actually maybe use two-layer, multi-layer perception that can still finish the job. So you can read the paper and maybe come to our poster for a detailed discussion. Thank you.
Thank you very much.